Okay, good afternoon guys. Hello? Madungog ba?
Dongog ra, sir.
Madungog ra, sir.
Okay, sige. Bago ni akong computer kay katong una na ambot nga ano to. Mo tong nagsige tagkahang kay wa na gyud nadaot na dayang motherboard no. Napugos kog palit, no. Labong nagdagino tag kwarta kay pandemic. Okay, so we will start right away kay taas-taas pa ni ato ang discussion. Okay, we will start with prayer in the name of the Father and of the Son and of the Holy Spirit. Hello. Okay. Creator of all things, true source of light and wisdom, origin of all being, graciously let our ray of your light penetrate the darkness of our understanding. Take from us the double darkness in which we have been born, an obscurity of sin and ignorance. Give us a keen understanding, a retentive memory, and the ability to grasp things correctly and fundamentally. Grant us the talent of being exact in our explanations and our ability to express with thoroughness and charm. Point out the beginning, direct the progress, and help in the completion. We ask this through Christ our Lord. Amen. Again, good afternoon, guys.
Afternoon, sir.
Afternoon, sir.
Okay. So, makita niya itong attendance sheet. Ha?
Yes, sir. Makita ra.
Okay. Today is 13, no? 13 karon, no? Okay. Abarkis,
Present, sir.
Abrasaldo. Abrasaldo, wa pa. Anchita, Arong,
Present, sir.
Darius,
Present, sir.
Elbistri,
Present, sir.
Cañete,
Present, sir.
Caballero,
Present, sir.
Castañares,
Present, sir.
Clemente,
Present, sir.
Cuyos,
Present, sir.
Dakay,
Present, sir.
Plaza,
Present, sir.
Sinopol, Sinopol wala.
Connecting.
Durham,
Connecting si Dinopol, sir.
ana si Donopol.
Oh, connecting, sir.
Okay. Durham,
Present, sir.
Cario Jan,
Present, sir.
Fabrique, absent. Iliana,
Present, sir.
Figueroa,
Fabrices are
Present.
present.
Fabrique na Fabrique.
Yes, sir. Sorry, sir. Wala ko madungog.
Figueroa, sir, present.
Okay. Jarina,
Present, sir.
Agroma,
Reconnecting po siya, sir.
okay. Leopando,
Present, sir.
Luwab.
Naa si Loob, sir. Present,
Okay. Sige. Lumibaw. Lumibaw.
Si Lumibo taon na excuse, sir.
Lumibaw na excuse. Muley. Muley. Wa si Muley. Murok.
Present, sir.
Nervida.
Present, sir.
Alice.
Present, sir.
Pito. Pipito. Perez.
Present, sir.
Randas.
Present, sir.
Ponte.
Present, sir.
sir.
Present.
Okay. Rubin.
Present, sir.
Sanoy.
Present, sir.
Denilio.
Present, sir. Sinilio.
Suson. Suson. Wala. Toledo.
Present, sir.
Vergara.
Present, sir.
Yaon.
Present, sir.
Okay. Kisa pa yung naabot ya ron be? Suson absent. Pipito.
Sir, Dinopol, sir.
Kisangan. Si
Dinopol. May class akong
Dinopol.
MSc. Akong MSc.
Adenopol.
Yeah.
Okay. Kinsa pa? Abrasaldo og si Anchita. Wala jud. Ha?
Si Muley, sir. Connecting pa, sir.
Yuli. Yuli. Okay. Okay, so that's it. Mag-start ano. By the way, shout out to Miss Abarkis and John, no, John Scario for getting a very high score in our quiz A, no, sa mass transfer. Siguro naglibog pa mo sa kuan, no, sa katong limiting reactants or limiting reagents, no. Importante din siya mga site because we will be dealing that.
Pipito, sir. Present. Pipito, sir.
Pipito na. Okay, sige. So daghan nakakuha no above 90 we have also Bilbis 3 also. Murag 89 siguro ni kuha Bilbis 3. Okay, kisa pa man tong kuan. I forgot the name sa uban no. Pero mga taga sa score ninyo uba I think only 5 out of 39, 5 or 6 ang below 60 points, no? 60 points ang ato ang passing by the way class, no? 60 points. Yes, 60% ang ato ang passing. Okay? If you get 90 above, that is already very high score, no? Okay. So, we will begin no, with our discussion. By the way, we'll be having our review na no before tamo dito na sa ato ang reactor designing no. Kailan na makasabot mo review sa takadiot kay ug di ta maka-review ani maglisod ta og kuan. We'll be having a hard time no in dealing our designing the reactor. Okay? So siguro mostly ang inyong teacher ani si Ma'am Bacalso siguro kay iha maning master nga subject yun no. Kining chemical reaction kinetics and chemical reaction engineering, no? So, what are chemical kinetics? Okay. Chemical kinetics is just the branch of physical chemistry that is concerned with understanding of the rates of chemical reactions. So, ang iha dihang involved niya sa chemical kinetics ang gikusgon ang iyang how fast or how slow is the chemical reactions. Mao na ang atong study ana niya sa regarding the chemical kinetics. In contrast sa ato ang thermodynamics, ang thermodynamics deals on it will only decide whether a certain reaction will occur or not, no? Pero ang sa chemical kinetics, ang iyang gikusgon, no? How fast or ang iyang speed, no? How fast or slow is the reaction that will take place. So that's the difference between thermodynamics and chemical kinetics. Okay, chemical kinetics, the factors that affect these rates kanang yang gikusgon or speed and the reaction mechanism by which reaction occur. So mo na yung study na to, mo na nga to ang nag-involve sa chemical kinetics. Reaction rates vary greatly. Some are very fast, like burning, no, and some are very slow, like disintegration of a plastic bottle in sunlight, no. Dugay kay na loy, it takes years, no, century, no. Then a reaction mechanism is the step-by-step sequence of elementary reactions by which overall chemical process occurs. We will also discuss this elementary reaction, very important, no, sa in dealing with chemical kinetics. Okay. So these are the things. Kinetics deals on how fast or slow does a reaction proceed. Thermodynamics, does a reaction takes place, meaning to say siyang mo determine kung doon na ba reaction nga mo takes place, no? Important factors which affect rates of reaction. Then reaction speed, ang kana siya sa kinetics, no? Okay. Important factors like reactant concentration, temperature, action of catalyst, which is very important because this is part of our study kining catalyst, and the surface area that involves the reaction, no? The contact area, actually the surface area is what is called contact area. The greater the surface area, mas capable of reacting, no? Kaya dako man siya area nga ma-react. Then we have also the pressure of gases, gaseous reactants or products. Kung mga gas, no, also liquids, no, pwede gihapon. No, studies the rate at which a chemical process occurs. So balik na review na to ni. Okay, ato na siyang i-fast forward. Then outline. So ato lang i-outline, no. Reaction rates, how we measure rates, rate laws, how the rate depends on amounts of reactants. So different man gud ang mga kuan, ang chemical reactions, no, and kinetics. So we have laws nga atong i-follow, no? Atong i-follow. Dili siya kanang generalized tanan, no? Okay? Nga usara nga to ang gamiton nga formula, dili. There are certain laws nga mo govern na niya, no? Okay? Now the integrated rate laws, we have also the integrated rate laws. Mirog kusar siya ba, no? Integration, no? We need to say how to calculate the amount left or time to reach a given amount. Okay? So ideally ang ato ang kuan din na mahurot, no, but actually in real life, in real situation, dili jud na mahurot, no, ang ato ang reactant for some reason na agi siya mahabili, no. Okay, we cannot have a perfect, no, or 100% product nga ato ang need, no. So kinahanglan na aratay certain amount nga makuan. So theoretically usahay ang ato ang pag-compute 100% atong gamiton, no, just for the simplicity of computation. Okay, so half-life, no, usually on some siya nga order of reaction, so we will talk about that later, no. Okay, the Arrhenius equation, how rate constant changes with temperature, usually mag-involve niya sa kining ato ang activation energy, no, magkailangan ta ang Arrhenius equation. So the mechanisms, we need to say the link between the rate and molecular scale processes. So mo na yung mechanism na niya. So all these things ato na ning nagian, no, sa ato ang subject sa chemical kinetics. Okay, so reaction rates, ato na ning i-summarize. So at the start we have red color, no, which is 1 mole of A. Now we have no, ang kanang blue color mo na yung mole sa B, no. Now at a certain period of time like 20 seconds, doon na forma nga B, no. And then labi na sa 40 seconds, no. As you can see, medyo nahurot ng, medyo nawawa na ang A. So 0.3 moles na lang ang A and then 0.7 moles ang B. All in all, maura gihapon 1 mole gihapon ang tanan. Aron dili ta ma against the law sa ato ang conservation of mass, no? Then the rates of reactions can be determined by monitoring the change in concentration of either reactants or products as a function of time t. But in general, ang ato ang basihan din na ang reactant ra gyud, no? Ang reactant ra gyud ang ato ang ideal during our designing, no? Okay, because o mogamit ta sa product, the same ra gyud siya sa ato ang reactant gamiton. So maglibog-libog na lang ta, ato na lang isulisod atong kinabuhi. So reactant ra gyud ang atong gamiton ana. Okay? Okay, for the reaction A to B, there are two ways of measuring rate. Okay. The speed at which the reactants disappear, the speed at which the products appear. Okay. So actually they are equal, no? And then reversible reactions. As products accumulates, they can begin to turn back into reactants. So usa sa atong study is the equilibrium constant, no? I'm not sure kung naapil ba na ako sa video or sa discussion ani. Kinahanglan ato sa atong ibalik yun, no? Aron watay gap sa ato ang pagkuan. Disunod na ta padulong sa finals. All the four reactors atong i-discuss, no? Okay. So, hopefully maka-discuss po ta ani kadiyot ning ato ang equilibrium constant. Then early on, the rate will depend on only the amount of reactants present. So sa sugod, no? We want to measure the reactants as soon as they are mixed, no? Okay? So actually dili pod mix, no? Doon na isa lang ka reactant, dissociate siya o mo change siya with time, no? Or with the reaction of air, no? Sa hingana. Okay? Then a general way of measuring the rate of the reaction is in terms of change in concentration per unit time. Okay, so mao na siya nga to ang general term, no? Sa rate, concentration per unit time or moles per unit volume per unit time. Okay? Now, instantaneous rate, meaning to say, ang ato magong rate sa reaction, dili siya pareho o gikusgon for a certain level of time. So that's why we have what is called instantaneous rate, meaning to say at a certain period of time pila ang iyang rate na niya. So mao na nga to ang equation na niya, no? We have a differential, no? Ang atong limit sa na niya d over dt na niya. Okay? So actually that is the change, no? Atong concentration then over change in time. Mean to say concentration sa ato ang reactants initial then less sa ato ang concentration at the final. Baliktad po diri sa kuan sa ato ang product, no? Okay? Our products have a positive value. Our reactants will always be a negative value. Okay? Disappearing man siya, no? Makanam siya kawagtan. Okay? Now, most common units, that is molarity per second. Or you can say number of moles per unit volume. Depende sa volume, depende sa gigamit. Okay? So, or concentration per unit seconds, no? Okay, in this case, kasagaran molarity gigamit, no? That is moles per liter. Okay? Or kilomoles per kiloliter. Okay? Pwede gihapon na. No? Now, where molarity, open na, no? So, pasa na to gamay. Okay, reaction rate is the change in the concentration. Okay. So, mao na ni siya, no? Now, dealing with concentration of A, ato ang rate diha is negative. So, okay? So, the change in concentration of A over period of time. So, that is the rate iyang gikusgon, no? Because we are talking rate, kinahanglan gyud tag time. No? Anything dunay rate, involve gina siya og time, no? Flow rate, mass rate, unsa din ang dunay rate niya, no? Kinahanglan siya og time. So, ang iyang concentration niya per unit time. So, mao na siya ang gikusgon sa iyang appearance or disappearance, no? Okay? So, in relation to concentration of B, positive siya, no? Positive siya kay appear man siya, meaning to say natao siya, no? Ning evolve siya, no? From nothing, no? Gikan sa A. Ang A nagkaanam og kahurot na formang B, okay? Okay, so So to generalize for the equation, we have a coefficient of A, reactant A with small letter a, and so on and so forth, no, until sa capital D, which is the species, and the small letter d as the coefficient niya, no, that is the number of moles. Kanang mga gagmay nga letter, that is the number of moles. Okay, so rate, ato ng kanang rate niya in terms of A, that will be negative. Now in terms of B, that will be negative also. Take note of our coefficient, which is the moles. It is also per, no, per unit sa atong concentration na kabutang siya din na. Kaya nga naman, kinahanglan naman gud ang atong ideal ani is that only 1 mole, no, only 1 mole ang ato ang para uniform, para dali ato mabasa, dali ato ma-compute. That's why kung doon natin mga coefficient niya, i-divide nato siya sa iyang coefficient niya, so that ang tanan nato dihang mga reactant involved siya og 1 mole lang, no, tag 1 mole lang siya. Okay, as you can see in our products, positive ang ato ang, like the C and the D. The change in concentration sa C o concentration sa D is positive. Okay, okay, so kini siya at nag-involve siya chemical. Notice that for every 1 mole of oxygen that appears, so mamaya to ang usa sa product. Now 4 times, no, as many moles of NO2 ang appear pod, no. Now in the meantime, twice as many moles of N2O5 will be disappearing as moles of oxygen forming. So magdugangan ang tanan, magdugangan na silang tanan. That's why very important sa tuwa ang limiting reactant, no. Kinahanglan kita kasabot unsa ang limiting reactant. Okay, ang limiting reactant mao to siyang substance nga maoy unang mahurot, no, maoy unang mahurot. Okay, so I correct the module because ang module dito ang nakabutang dito is, ang correct niya is in excess ba itong nakabutang dito, which is wrong, no. So anyway, don't worry about our exam kay, because ako gina siyang reviewon, no, na-review na nako, gi-change na nako yung score dito. If you have still complaint or any comments, no, just for me, no, kung napamoy na basig na ako na alingkatan dito. Okay, okay, so same reaction cannot have 3 different rates. So kaya nga naman ang disappearance sa usa mao appearance pod sa usa, no. Ang na-disappear ang usa meaning nagkaanon siya kawagtang, na at the same time mo appear doon ang mo appear siya. Kung dili gani na magkapareho ang ilang rate na nila, will be against the law sa to ang conservation of mass, no. No, dili na siya pwede, no, asam din pa dong uban, no, kaya na siya. Okay, okay, so mo na itong pag-rate. Okay, so the rate is this one is negative para sa reactant man siya, this is N2O5. The change in the concentration of N2O5 per unit time, no, per the change in time, no. Okay, is equal, no, is equals to the appearance, no. Like the NO2 kay kuan man siya, do naman siya 4 nga coefficient, so divided by 4. Okay, also with the oxygen, no, wala man siya kuan 1 man lang yung coefficient, so di na necessary na ibutang iyang 1 diha, no, divided by 1. Okay, so mao na yung pagsuot niya. So take note, equal na sila, meaning to say at ning kuan siya, no, kana at the instant nga ang atong NO2 nahilis or kana siya kagkuha, instantly pud na porma ang NO2 ug O2, no. Dungan, no, dungan gyud sila tanan, dili siya pwede nga aguna ang NO2 ka hurot unya pagkahuman wala pa na porma nga kuan, no, dili siya pwede, no, dapat dungan sila. Okay, so here are some examples for this one in graph, no. Importante pud nga actually if you know how to read a graph in kinetics, dali ra gyud niyo ma-understand, no, ang iyang reaction rates, no, because we will be making sure nga ato ang graph is a straight line para dali masulbad, no, and there are many ways to make that into a straight line, no. Kung dili gani siya may straight line, nag-curve siya, ato na siyang himon nga straight line. Kinahanglan may straight line nato siya. Then that's a time Sayo na lang to pag-compute ang reaction kinetics, no? Sa usa ka reaction. Okay? So for this one, Br2, no? Br2 plus HCOH, and then atong average rate, gikuha lang niya nga to ang slope, no? For every rate, saka nagkurba man gyud siya, no? Gikuha lang niya ang average. And then pareho ra tanan, no? Rate at 1 second, and then for every second, no? Gikuha niya ang iyang kuan niya rate. So remember that concentration is the initial concentration sa reactant, ha. Okay? Yeah, you can also, kung gamiton nimo ang final kuan, make sure nga doon na kay butang nga negative kung kuan siya, kung kanang sa reactant siya. Pero kung sa product, remember nga positive siya kay nag-appearance man siya, nag-appear man siya. Okay? Take note lang kung doon naman siya time nga mag-equilibrium siya, meaning to say nga to ang atong product nibalik na po siya ngadto sa reactant, forming a reactant og balik. So doon na po tayo ingon ana, no? Okay? But general form na to, general na tong statement is that ang atong reactant positive siya, ang atong rate sa ato ang reactant is negative, ang atong product positive. Okay? So this is the general equation, no? Taking the average for Br2. We have the final and the initial because we're dealing on the reactant side. So negative na lang ito ibutang. Pero kung di ka magbutang sa negative, you can do the initial minus final. Automatic siya mag-negative, no? Okay? Then instantaneous rate for specific instant in time, meaning to say at any given time, no? Instantaneous man. Okay? Importante po na siya. So moingon ta nga pila may ang rate at 250 seconds. Okay? So yun ato na siyang kuhaon diha ana lang nga rate, no? Because ang rate dili parehas sa for every time, no? Dili sila magkaparehas. Okay? Okay. So ang slope lagi kuha, no? We have also this one, rates of the reaction between molecular bromine and formic acid at 25 degrees Celsius, no? Maghihapon pwede na ito na sila i-graph, no? At this time straight line na siya, no? Okay, so dali na lang siya tumato ang pag abutang sa equation. Okay, like this one, no? Okay, so kay straight line man siya, meaning to say wala man siya ga-curve. Okay. Okay, so factors affecting reaction, reaction rate constant. Okay, we have temperature, no? Okay, so we'll be dealing with the collision theory. When two chemicals react, the molecules have to collide with each other in particular orientation with sufficient energy for the reaction to take place. That's why surface area is needed, no? Also kinetic theory, increasing temperature means molecules move faster and will collide more, no, to each other. Okay, so the collision theory, in simple terms, the more you collide, the more you react. Okay, so that's it. Then concentration of reactants. As concentration of reactants increases, so does the likelihood that reactant molecules will collide. Okay. Catalyst, very important, no? Speed up reactions by lowering activation energy. Kung taas ang activation energy, kinahanglan nag-catalyst, no? Para siya maubos ang iyang activation energy. Okay? Sa iyo naman pag-unahan ng activation energy, you just think of a mountain, no? Bukid. Tapos, siyempre, kung mo padulong ka sa pikas nga area, the opposite side of the mountain, kailan kagyan kung dili mo sakag ka sa bukid. Okay? So very very stressful, no? Taas kay kaglatason, no? So mo na siyang, so hinay kay imong reaction, hinay kay ang imong pagkuan kay dako pa ka og latason, no? Taas kay kagkuan. Pero kung mabutang ka og catalyst, kanang mountain niya ng patagon, no? Murag patagon niya. Nato dili mapatag niya, medyo maubos-ubos, mamumubo ang iyang mountain. So ang imong pagsaka gamay na lang. So in that case, mukusog ang imong reaction. Okay? And also catalyst will be consumed first, no, in our sa elementary reaction na to, ang catalyst ma-consume din siya, and then at the end of the reaction ibalik ra pud siya, no, so mabalik ra siya. In other words, catalyst mura siya wala mo participate sa reaction, no. Okay, actually it did participate, no. Okay, mabalik lang siya, no, mabalik lang. Okay, surface area. So, more area for reactants to be in contact. Okay, so ato na lang na-discuss ganiha. Then, okay, pressure. Importante niya, for, especially for the gaseous. Also, some liquids, no? Importante po ng pressure. Okay? Because the more you exert pressure, no? It will increase the number of collisions. And remember that more collisions, more reaction, no? Mas daghan ang tendency nga mag-react sila. Okay? Reaction rate examples. Okay, so ako pa din yung gi-appeal. Sige, ato lang gi-appeal ni. So, we have time here in seconds. And then we have concentration in molarity. Sa to ang right side, no? In this reaction, the concentration of butyl chloride, which is the reactant with water, no, was measured at various times T, no? Okay, so mo na niya ni tabo niya, no? So average rate, we have the change in concentration, final minus initial or initial minus final, depende kung katigo ka mo gamit sa imong units, no, sa imong positive or negative sign, no? It doesn't matter, no, basta katigo ka mo gamit, no? Okay, so 0.1 minus 0.095, that is the concentration or molarity over 50. So ang primero ni, no, ang primero na to ni, and so on and so forth. Okay, so ito lang kung ano yung average. Okay, now average rate na ni siya ang primero ganiha, ito balik niya din ni 1.9 times 10 to the 4. Okay, so note that the average rate decreases as the reaction proceeds. Okay, so from 1.9 nahimo na siyang 0.56, no, sa pinakatumoy, pinakaubos. So nagkaroon siya kagamay. Okay, now this is because as the reaction goes forward, there are fewer collisions between reactant molecules. Siyempre, nagkaano naman siya kahurot, no? Na-form naman siya into product. So, ang atong reactant, nagkaano mo kagamay. Okay? So, so this is the things. No, mga nakumbot pasabot nga kung curve nga to ang kuan, dapat katigutaan sana to siya pagpatuloy. There are techniques na niya, no? Which included in this instruction, video akong gipili nga mas maklear ninyo ang pagsabot unsa na to pag making the reaction rates simpler to understand, no? Okay. Now the slope of a line tangent to the curve at any point is the instantaneous rate at that time. Okay, usa ra man gyud ang modapat ana ning straight line, no? First doon na kay curve line, and then mag line kanyang tangent, no? Believe it or not, usa ra gyud ka point ang maiguan niya, no? Usa ra gyud ka point maiguan niya. Okay, so that is the slope of line tangent to the curve at any point is the instantaneous rate at that time. Okay, so how to do it? You have to get the integration, no? Okay, okay, so the reaction slows down with time because the concentration of the reactant decreases. So balik na siya diyan, no? Okay, okay, the stoichiometry, no? In this reaction, the ratio of CH4H9Cl to C4H9OH is 1:1. Okay? So makita man nato sa to ang chemical reaction, no? Equation, no? Ang iyang coefficient sa ilang moles 1:1 ra gyud sila. Okay. Now, the rate of disappearance of C4H9Cl is the same as the rate of appearance. So pareho ra sila kay wala man sila iko ano. Pareho ra lag number of moles. Okay? Okay, so we'll do the reaction rate loss. Okay, now each reaction has its own equation that expresses its rate as a function of the concentration of the involved species, no? like reactants, product, catalyst. No, marog yan tulo kasagaran, no? Okay? This is called rate law. Okay? Now, balik ko na to, each reaction has its own equation. So, dili sila pwede pare-pareho og equation, no? That expresses its rate as a function of the concentration. So, kaningon tag expresses its rate as a function, mo ni siyang integral law na niya, no? So, tanan, pas tanan niya. Pero doon na sila kagaling yung kadausan nila, no? Depende sa klase sa reactant, sa product nga ma-form, o sa catalyst nga gigamit. Okay? Okay. So, in general, rates of reactions increases as concentrations increase, since there are more collisions occurring between reactants. Okay, so rates of reactions increases as concentration increases. The overall concentration dependence of reaction rate is given in a rate law or rate expression. For reactions, follow simple rate laws. So, sa man eh. Mga na siya, no? And so on and so forth. Okay? So, kung basahon nato na siya nga to ang rate law, doon na tayo constant diya nga key, no? Then we have concentration of A raised to the exponent M and B raised to the exponent N and so on and so forth, no? Meaning to say, ang ato ang A is at the M order, no? Ang ato ang species nga A. Ang ato ang B is at the N order, no? Para lang niya, no? Pero the overall reaction, imuhara nang i-add, no? Kanang M ug N, i-add nimo na siya, and then that's the overall reaction, no? So kung duha rang ato ang species nga nag-involve sa reaction A ug B lang, now ang ato ang order of reaction na niya kung mo take place ang usa ka reaction, ang order na niya i-add na to ang ilang exponent nila, no, like the M plus N, no, i-add na to. So mo na iya to ang overall reaction order, no, mo na siya nga to ang order. But with respect to ang order sa to A, ang iyang order niya is kanang M lang. Okay? So kung 2 na ang iyang M diha, betan M is equals to 2. So ang A na to, species A, is at the second order. So likewise kung atong B, ang atong N diha is 1, so ang atong B is at the first order. Okay? Ang overall reaction niya is 3. Okay? 3 ang iyang order. Okay. Okay, so ayan B reactant concentration, the expression reaction order. Okay, so as I said, no. So while the constant key is the rate constant, and the overall reaction order is the sum of the reaction order, so M plus N. Okay. So rate laws. Rate constant and orders are determined experimentally. So meaning to say, before, long ago pa, no, ang mga scientists they are proving the rate laws by experimenting, no? So gi-experiment na nila. So happy na ta karon kay kita, wala di na ta mag-experiment ani nila, no? Ato na lang gi kuha ang ilang kuan, no, ang ilang na experiment, no? Okay? So mga kulba ang mga tao sa una, no? Lisod nga process ni siya, okay? And they were able to experiment something out of nothing, no? Ang kita na diha, no? That's why dali lang sa to makabuhat og vaccine kay na naman diha nang tungkuan. Okay? During the time nga Spanish flu, walay vaccine adto nga time, no? Okay, nag-mutate lang ang virus into a lower kuan na, no? Medyo nanghinay ang iyang virus, no? Nadugay, so no, nawala siya after 2 years, no? After 2 years nawagtang ang Spanish flu, pero daghang patay adto nga time, no? So mao po ni siya, no, involved siya ani. Okay? Sa karon nga time, dali na lang ang vaccine na buhat. Okay? Now the order of reactant is not generally related to its stoichiometric coefficient in a balanced chemical reaction. Okay? Okay, so it's not generally related to its stoichiometric coefficient in a balanced chemical reaction. Okay, so for this one, no, fluorine gas, no, we have reacted to pareho ng gas na no, ClO2 gas, ato if ClO2 is also gas. So kung tanaw na to nga to ang kuan coefficient nila, makasulti ta nga daghan ning ato ang if ClO2 ning product na to no, asa ning ClO2 gas no, kay usara ang ring at if to gamay ra ni siya, kay usara man siya. Okay, but the order of reactant is not generally related to its stoichiometric coefficient, no. Okay, so ang ato ang order sa ato ang reaction is this one, no. Ang atong gibasihan as I said, ang reactant lang, no. Murag way appeal ang ato ang product, so reactant lang ta but you can also do the product, no. Baliktaron na to, pwede gihapon to gamiton siya. Okay, but in dealing things in kinetics, importante ang ato lang reactant. Okay, so we have F2 with a coefficient of 1. How about ClO2? Doon naman siya ito. So 1 atong ibutang. Okay, 1 ba ito ibutang or 2? Not necessarily, no. The order of reactant is not generally related to its stoichiometric coefficient in a balanced chemical equation. Sahay dili o sahay pod mao pod, no. Depende lang sa kuan reaction. Okay, dili siya automatic, meaning to say dili automatic. Do ang iyang kuan coefficient to na podbutan to din. Not really, no. Okay, now reactions with simple rate laws. Okay, H2 plus I2 plus 2HI. So ang ato ang hydrogen diha is concentration sa atong hydrogen ug iodine is ang ato ang power niya is 1, no. So overall order is 2, no. So ato ang 3ClO2 negative mao gihapon. As you can see, ClO2 negative 3 ang iyang coefficient, pero ang atong power dia is in second order, no, ang ato ang reaction. So dili necessary, no. Now reaction with complex rate laws such as H2 plus Br2, then we have 2 HBr. So as you can see, ang ato ang reaction is this one, no, sa ubos, no. Complex siya, no, kay gi-appeal na to ang ato ang HBr. Okay, so ang ato ang rate laws magdepende, no, sa klase sa reaction. Nganong kanami atong gigamit, nganong di man pwede ning gamiton ngana, no. Magdepende siya sa actually sa ato ang reaction, no. Okay, so imply multi-step reaction sequence of, that's why ang yana nga ato ang reaction kay ato ning gi-appeal sa atong discussion, no, nganong kinahanglan nato siya, kung kaya dapat importante nga makatigot ta sa elementary steps sa ato ang reaction, no. Matinga mo nganong ning ana may reaction na niya. Okay, so but if you know the sequence of elementary steps, masabtan niyo mao day ana di siya mao day. Okay, so we'll do that, no. Anyway, this is review man lang, no, pero akong gi-appeal din sa ato ang discussion. Okay, so elementary reactions, we have this one, unimolecular decomposition, meaning to say usa lang siya. So A, like A, ipadulong ato sa B. So ang ato ang rate expression diha is concentration sa A, no, then raised to the power of 1. Now sa bimolecular reaction, meaning to say duha ang atong reactant into product. So okay, so A plus B, pwede ta mag-concentration sa A din concentration sa B kung pareho nga mga reactant, o pwede ra squared na to, no. Okay, this is very simple, no, simple siya. Ang complex may lisod, no. Now reactant order reflects molecularity, number of molecules involved in reaction. So molecularity, it is the number of molecules involved in reaction. Okay. Now examples of reaction rate laws. Okay, we have saan nga time ron. Okay, because we will cut this at 4 p.m. Okay, consider the following reactions: ammonia and then NO2. Okay, so let's say that the following observation from several experiments were made. Okay. Now, as ammonium ion doubles the rate doubles uh, with denote as constant, no? So atong i-double, so what will happen? Okay. As inoto doubles the rate doubles with ammonium. With ammonium ion constant, no? Now the rate of this reaction would be expressed as, okay, so mao nang magawa sa ato ang reaction. Okay? Maglibog taon sa may atong i-double. O i-double nimo ang iyang ammonia, unya order 1 raman siya. Okay? Mo double ra pod siya, no? Mo double ra pod ang iyang rate. Saka ra pod kaduha ang iyang rate. Okay? Likewise mao pod ang inoto because they are in first order with respect sa ilaha lang, no? Second order silang tanan pero sa ilaha lang usa lang. So, meaning to say, kung ang ammonia himo i-double nimo, let in auto constant, no? I-constant nimo siya. So, unsa may mahitabo sa ato ang rate expression? Sa ato ang rate mo double ra siya, no? Igo ra siya mo double, no? Okay? Likewise, mao pod ang inoto. Kung ato siyang i-double ang inoto, then making ammonium ion in constant. So what will happen to the rate? Mo double ra pod siya. Okay? Now the actions to be first order with respect to as I said, no, akong gibutan ng ganiha. Also sa inoto, okay? But the overall order of the action is said to be second order, no? Because 1 plus 1 is 2 man, okay? Reaction rates come from experiment data, not stoichiometry. Okay, so experimental gina siya, no? Ang ato diri ato na lang ning copy, no? Gi-copy gikan sa mga scientists sa unang panahon. So example reaction rate, concentration and rate, so mga experimental man siya, no? Kamo aning nigawas nga values nila. Okay? Okay. So likewise mao gyapon ni siya. Okay, so rate is directly proportional to ammonium ion, also within auto, also both, no? Okay, so this equation is called the rate law and key is the rate constant. So balik na siya, no? Ato lang gibalik. Okay. Okay. So gibalik na ni nato. Overall reaction is second order. Okay, so integrated rate laws. So express concentration as a function of time. Then Y, experimental data is typically in concentration versus time. How? Integrate the expression of rate law. Okay. So for example, you have your reaction A, reactant A, and then forming into product, and your order is 0. So in differential form, your rate is just equals to negative K times 1, no? Times 1 kay any number raised to the exponent 0 is 1 man, no? Okay, so very pinakasayo, no? So more na integrated form, we have the concentration of is equals to initial, no? Final. By the way, kanang A nga wala siya suffix, no? Kuan na siya kanang final siya, no? Katong O initial to. Okay, so mo na iyang expression niya. Now for the first order, doon na tayo concentration sa A. I-double na to ang kuan na to niya, i-double na to ang ato ang concentration sa A, mo double ra pod ang ato ang K. Okay? So the integral form is d over dt. We have concentrations of ln A atong gi-separate ang ato ang kuan, no? Initial ug ang finals. Okay? So ln, so mo na yan makuha na to. Anyway, we will discuss this. Doon ay video nga akong i-video ni mas klaro ninyo masabtan ang iyang kuan, no? It will be very hard for me to discuss in this manner, no? Okay? So okay, we'll just proceed so that we can do the video, no? Simple example reaction. So this one, So dE over dt. Kanang A diha concentration na ha. Remember the concentration na siya no. So nagbawog siya no. The technique diha in ato ang modeling ato ang kuan sa ato ang graph kinahanglan matulid nato na siya. So we will do the natural log no. 1 over natural log or just simply natural log. In that case ang ato ang line mag-straight line siya because sayo na lang to kuha ng atong slope no. Slope is the rate man. Okay? Rate of change dE over A. So the change in concentration over the change in time. Okay? So kanang kuan diha gamma is degradation constant. So mo na lang siyang diferensya nila no. Example, chemical reaction that models generation from D and degradation of molecule A. So duha siya no. Generation D ang degradation ang A molecule A. So this is between A and D. Okay, the rate of change ang atong gamiton diha ang ato among reactant which is the A. Okay. So production constant which is the D. Degradation constant which is the gamma no. Okay. Example chemical reaction that models generation from A and B also no. Of molecule C. So again, mga atong kuan na to no. Example chemical reaction that models generation from A and B of molecule C. Okay. So mo in general kuan niya, general formula niya do not take coefficient, do not take power like for example negative K times the E raised to the exponent N and then B raised to the exponent M. Okay? So again, pwede ra ka magkuha kung duha ka buok ng imong reactant A and B, pwede ra usa ra imong kuha ano grade ana niya no. Ang ato arang A or ang B ba depende. Why? Because they are just the same no. Ang reaction niya pareho lang no. Ang pag-react niya sa usa mao po'y paggawa sa usa no, pag-form sa usa. So pareho ra na sila. Okay. Order of reaction so muna ni ato na ning agi ganiha. So we have 0 meaning to say if the change in concentration of the reactant produces no effect. So wala ito effect no kay any number raised to the exponent 0 is 1 no. No, ang first order mo double lang siya no. A reaction is first order if doubling the concentration causes the rate to double. So mag-double ka sa any concentration ang iba o ang B ba depende no. Or tulo ka buok A plus B plus C nya mo gawas nato nga product is D. So any of the three no. In dealing with order kinahanglan ang duhaan na pitan A imong gakuhag order sa may mo doble baron ang A. Dapat ang B ug ang C constant ang ilahang value no. Okay, hasta ang imong di ang product ang imo lang gitandog diha ang imo to lang gi-change diha is that we double the concentration of A. Now what will happen to the rate? Now kung first order siya ang ato ang chemical reaction or ang atong rate niya mo double ra siya pod. Okay, ang atong rate no. Okay, likewise kung ang B pod atong i-double making A and C constant, also the D constant ang iyang gawas niya, what will happen to the rate? Mo-double ra pud siya. Okay? Mean to say ang iyang gikusgon no. Mukusog siya no. Mo-double ang iyang gikusgon kay rate man no. Okay? Now second order difference siya dako kay glukso no. Now i-double nimo ang any species like the A, i-double nimo then making other as constant, ang rate niya mo quadruple no. Grabe ang iyang pagsaka no. So gidouble nimo ang kuan concentration sa usa pero ang atong rate ang katong R ba no, ang atong rate expression na ang iyang gikusgon niya mo quadruple no, mo quadruple. Okay, third order. Okay, doubling concentration leads to 8 times no, 8 times katulo siya mo kuan no. So dili lang mo quadruple mo 8 times itawag na niya no. Extremely rare no. Kasagaran gyud sa ato ang good kuan reaction nara sa first first second order no. Tagsa ra mo gawas ning third order no. During the design sa ato ang mga reactor nara gyud sa 0 first ug second order no. But sometimes we also have problems involves third order reaction. Okay? So mo na ning nagawas nga ganiha no. Ang mo na final mo na siya reason na niya katong kaganiha tong gihatag. Okay, the zero order humanataan ni. So okay, so this equation has a general form of a straight line. Y is equals to mx plus b. As I said, no? Kinahanglan na to nga doon natay straight line. Because ang our slope, mo na siya ang ato ang constant key. No? Ang atong slope kanang letter M, mo na siyang slope, mo na atong key. So, masolve na to ang ato ang key directly, no? Kung doon natay straight line. Pero, kung dili gani straight line siya, maglisod tag-solve sa to ang key, ang ato ang constant, no? Okay? So, kung zero order lang siya, directly ang ato ang y diha is concentration of A. Kung ang ato ang time, direkta lang is time. Okay? Now, on the second order, the first order process. Okay. So, mo na yung reaction, no? Atong i-natural lag ang A. Because kung dili na to i-natural, dili na to i-lag ang ato ang concentration sa A, dili ta kagawas og straight line. Okay? So, ang forma na niya for first order reaction is natural lag na to ang concentration sa A and then morning magawa. So, ang kanang key diha sa expression na to nga y is equals to mx plus b. So, ang atong y diha kanang lna, mo ni y na to. So, ang atong mx, so kanang m na to is the negative key. Ang atong x mo nang t. Okay? O ang ato ang lna mo na siya ang ato ang intersecting point, no, at x equals to 0. So mo nang ato ang b. Okay? Okay, so nabay graph na ko nabutang din hi. Kiwa na ko ang butang graph. So this equation has the general form for straight line. Okay? Y is equals to mx plus b. So a plot of ln a versus t is a straight line with a slope, negative key, and intercept in ln o. Okay. So, okay. So, ang difference sa ani gani nga graph, ang ato ang straight line din karon is the natural lag of concentration of A. Ang kaganiha, katong sa zero order, wala nang natural lag, concentration lang diretso. Okay? Second order. Okay, first example man no? First order example. Okay. So, mo na iyang general formula, no? Natural lag. And then, pwede na ito na bali-balihon na itong equation, no? Pabaitan magkuha ta sa constant lang. So, sa may ato ang gamiton ng equation, okay? So, masolve na nato, no? Now, for example, this one, no? Okay, so, the final concentration or the concentration at time t, instantaneous time, is equals to the initial concentration. So gibali man nato, no, gi natural lag gikuha man natong kuan sa mogamit ta og e, no? That will be result exponent kt. So I guess you already know how to in your mathematics, in your algebra, no? Kung saan nato pag bali-bali sa equation, kung saan to paggamit sa natural lag, no? Okay? Now, when ln is plotted as a function of time, a straight line results. Okay? So, kung dili mo gud nato siya ang sa second order, ang sa first order mo gud, I mean sa first order, o dili nato siya i natural log, like for example this in the left side, no, in the left side curve ang iyang mugawas, which is very hard for us, no, magkuha tag mga average, dugay kaayo ang pagkuha niya, no, dugay kaayo ang pagkuha nato sa kuha na kay magsige tag average for every point, no. Whereas kung i-natural log nato siya, mo na ning sa right side, mo straight line siya dito. So ang atong equation na niya is mo na nang doon na tayo natural log. Okay? Second order. Okay, for second order, 1 over concentration sa E ang atong gamiton so that we can have a straight line, no? Mo itong gamiton nga pero baliktad ang iyang kuan, no, from low to higher, no, baliktad ang iyang pagka-straight line, no. Okay, so ang atong slope is positive key na, dili na negative, no. So as you can see, ang atong gigamit is 1 over watay natural lag diri, no. Concentration siya is 1 over A. That is the second order. Usually naani siya sa ato ang mga half-life gigamit, no, equation. Okay, so mo ni siya, no. How to determine the reaction order? Basahon na nimo nato ning graph, no, at a certain time, no. Usually kung doon natin mag-graph nga mga tulo ka dita or 4 ka dita, mabasa nato dayon. So this one, pwede lang siya i-graph diretso. Okay, and then kuhaon nato kung mo-curve gani siya, then that ato na po siyang in-natural log. Kung curve gihapon siya, ato na po siyang 1 over concentration. Okay, siya ro dili may straight line, madugay, no. Okay, so dugay siya, no? That is to determine the reaction order. Okay, graphing LNOT versus T yields this one. So naka bawg siya, no, naka kuan siya. So ang ato equation nga LNT does not fit kay ngano man dili mo siya straight line, dapat siya mo ka straight line siya. Okay, so ano mo straight line. So the plot is not a straight line, so the process is not first order in A. Okay, so ato ta mo graph sa second order, tanan nato mo kuan ba. So unsa tong second order? 1 over concentration of A. So second order process, so ang graph niya ni tulid na, no, straight line na siya, no, nya sakto pod from lower to higher, no, as the time progresses ning taas pod ang iyang concentration. So mo ni tong gamiton nga equation. So 1 over, so this actually is the half life, no, mo ni gamit sa mga half life nga kuan equation. Okay, so this is a straight line, therefore the process is second order. So that is how to find the order of the reaction, no. Mag trial and error ka, mag graphing ka. Okay, okay, half life, no, because half life, so the order maglisod ta, no. First order mao pod ang iyang reaction niya. So sa second order yung pinaka the best sa ato ang kuan sa atong half life, but you also have half life in third order, first order, and second order. So ang formula niya maglahi-lahi, okay, and you have to memorize all these formulas, no. Kini mga half life nga naa sa zero order, half life nga naa sa first order, and the common one which is the second order half life, which is the most commonly used, no, labi na sa atong mga kining mga materials nga kuan siya, no, mag isotope, no, isotope. Okay, gigamit sa nuclear. Okay, then half life is the time taken for the concentration of a reactant to drop to half of its original value. Okay, so katunga sa iyang kuan nawagtang na, no. So pila ang time, no, pwede seconds, pwede minute lang, or pwede century, no, daghan kaayo, no, depende ra, no. Okay, now substitute into integrated rate laws. T 1/2 is the time taken for A to reach 1/2 concentration originally, no. Pwede ra, depende sa kuan, no, depende sa gigamit pud nato ning half life sa pag-solve sa to ang key kanang constant key. Okay, note, for a first order process, the half-life does not depend on concentration. So, tanaw na to ang first order, wala siya value sa concentration, no? So, in other words, wala siya nag-depend sa concentration sa initial concentration sa species nga sa reactant, no? Wala, no? Okay. Now, first order process, okay, first order process, sample din nato ni, no? Okay, sample. So we have our final concentration natural log is equals to, so ato na siyang gikuan ang equation niya sa ato ang kuano katong ka-graph nato sa first order straight line. So baliho-balihon ta lang na siya, and then kuhaon na tong half life niya. Okay, so KT at 1/2 half life, So ang mga tabuan niya, we have our final equation which is 0.693 over k equals half-life, no, t 1 half. So remember na kanang nga t 1 half is half-life na. Kanang dunay t niya subscript ka og 1 half. Okay? What is the half-life of okay, ato na example, no? We will not be discussing this one. You are going to see this one sa ato ang video discussion, and then i-download ninyo ni, inyo makita ninyo ni, no? Anyway, doon na ato na siyang giapil sa ato ang video discussion karon nga naka-include aning ato ang PPT, no, atong PowerPoint. Okay? So first order reaction, A to product, so number of half-lives, so mao na ato ang data. Okay? Now note, for a first order process, the half-life does not depend on the concentration. Okay? So first order. Ang atong gibasihan diha ang kanang natural log sa 2. Okay? Mo itong gigamit ana ni. So this is the general equation sa atong half-life sa second order. Okay? Now equations of reactions of various orders. So in kinetics mo na ning mga equation niya, no? Okay? So rate law, sa zero order, rate is just equals to key sa constant, sa rate constant, no? Concentration o sa time equation, na po gibutan na. So pwede ra to ni siyang memorize ninyo. So pwede ra pod, no? Okay? So we have the half-life. Now ang unit niya mo importante kung unsay mga unit anin niya. Okay? Unsa may unit aning rate sa ato ang first order, unsay unit sa ato ang rate sa ato ang second order o zeroth order, no? Sa mga unit na importante pod, no? Because you will understand the kini siya second order ni. Pagtan-aw pa lang ninyo sa unit, kasabot na mo nga kini siya second order ni. Okay? Third order ni siya or first order ni o zeroth order ni. So pa sa unit makita na siya daan. Okay? Okay, so this is the rate loss. So marin na lang na siya. So ganyan dito. Okay. So reaction mechanism. What time na? Okay, so ato lang paspasan, no? Anyway, review naman natin siya sa kuan because we will do the sequence of the steps that lead. So this is the elementary steps or elementary reactions. So ato po ning gi-appeal na po din sa video nato, no? Okay. So okay, so we have our product. Our goal, no, is to make 2NO2 gas plus O2, and then the product, the final is 2NO2 gas. Okay? So actually before tani abot diha doon na tay duha ka elementary steps, no? Before taning abot sa 2NO plus O2 and then 2NO2 gas. Okay? Okay. Rate loss and rate determining step. The rate determining step is the slowest step in the sequence of steps leading to product formation. That's why kinahanglan ta og elementary reaction. Okay? Dili pwede wala. Dili ta kinahanglan katigot ta mo gamit ani niya. And that's why very important sa to ang reactor designing, katigot ta ani, no? I realize nga dapat i-review nato sa ni, no? So we'll have only 1 or 2 days to review this one, no? And I believe tomorrow is holiday, so dili ta pwede magkuan ugma. So maybe ato ning ma-continue sa next meeting na to karong Thursday, no? Okay? So the sum of the elementary steps must give the overall balance equation for the reaction. Okay? So ako na lang gi-upload sa video ang elementary. Nangita kog video nga kanang nindot na dali sabto ng elementary steps, no? Okay? Ang wa pa na ko ma-include dito ang ato ang amount of moles nga natanggal, no, gikan sa reaction. So ako na lang i-apply po na maybe by Thursday na lang, no? So sa karon sa ang ato sang mga rate loss ug ang atong mga how to deals with the making an equation, no, sa atong half-life, sa ato ang general equation sa atong mga rate laws. Okay? So, reaction mechanism. Okay. Okay, okay, so we have the elementary steps and then we have the molecularity, okay, which is the number of molecules present in elementary steps. Okay, very important, no? Then we have unimolecular, bimolecular, okay, and then third molecular, which is much complicated, no? It is uncommon to see thermolecular processes. Statistically improbable for an ineffective collision to occur. So kasagaran ko to data sa bimolecular, no. Pero ato lang gihapon na siyang gi-appeal, no, kanang thermolecular. Okay, next step. Sa to ang elementary reaction, no. Okay, so mo ni ato ang rate laws of elementary steps. So again, atong law of mass action, importante na siya. So mo ni siya nga ato ang elementary steps. Okay? So, unimolecular from A to products, then bimolecular A plus A to products, then bimolecular A plus B, duha man kabuk. Actually, the same species, pero duha man sila. So, that is bimolecular. So, we have the thermolecular, which is the hardest part. No? Okay? So, because kung thermolecular ka, ang imong rate order nimo diha, the order of reaction is very high, no? Which is very very complicated. Okay, so notice that the coefficient is become the exponent. Okay. Okay. So intermediates are species that appear in the action mechanism but not in the overall balance equation. So kinahanglan katigot ta mo kita kung kinsa ang si catalyst, kinsa dili ang catalyst, no? Ang intermediary lang, no? So duha man gud na, no? We have also this one, elementary steps. Ang na-cancel na to ani into auto. Ang mabili na to is NO. We have also NO, no? 2 in auto cancel. So 2 NO ang nabili og usa ka oxygen. Good. Okay. So Plaza A, Plaza cars slows at Plaza A. Okay. Then cars slows at Plaza B. So example of slow and fast action mechanisms. So we have this one, the slow initial step. Wait, atong time. 4:14, so 1 minute more. Okay. Tapos pa sa gamay. So the rate law for this reaction is found experimentally to be rate is equals to K in O2. Now carbon monoxide is necessary for this reaction to occur, but the rate of the reaction does not depend on its concentration. So CO is necessary. Kinahanglan mo form of carbon dioxide o nitrogen oxide. So the rate is equals to K and then ang gibasihan nato ang ato ang in auto, no? Second order siya. Okay. So first step. Okay. Then ang NO3 gi-consume siya on the second step. So as CO is involved in the slow, rate determines it does not appear in the rate law. Okay. Okay, anyway, ato man ni siyang ma-discuss, no, sa ato ang kuan. Ako lang gipakita ninyong slide so that ma-review ninyo once ma-download niyo ang video, mabasa ninyo, ma-review ninyo. Okay? Okay, so pulo na ni siya sa ato ang kuano, sa ato ang rate laws for multi-step reactions, apil na po na siya. So we will now proceed with our reaction, ato video discussion because for else ma-short ang atong time, no? Ako na ning time ang ato ang kuan discussion. Okay? So we have only until 6, no? So so rate laws for multi-step reactions apil na dito sa ato ang video discussion. Maybe mubo naman lang ni siya nga kuan PowerPoint. So we'll proceed sa ato ang video, no? Wait ha, kadiyot. Okay? We'll just proceed that next meeting sa ato ang kuan. Okay? Because wala pa man ta maka duha ni ka meeting ato ang kuan review, dili pwede usara. Okay? So we'll proceed with the video discussion, no? Para mas makatigom mo. Okay?
In this video, we're going to talk about chemical kinetics. We're also going to talk about reaction rates and also how to write the rate law expression using the initial rates method. So you might be wondering, what is chemical kinetics? Well, chemical kinetics is the study of reaction rates. It tells us how fast a reaction can occur. So we're concerned with the speed of a reaction, which is quite different than thermodynamics. In thermodynamics, we're concerned if a process is spontaneous or not. Will it occur or will it not occur on its own?
Okay, wait ka dito ha. Muna akong kakuanan sa ako ang computer. Mag-upload.
This is a spontaneous process. The free energy change of the reaction is negative, which tells us that it's spontaneous. However, in real life, if you were to take a piece of diamond, you wouldn't notice any change from diamond to graphite. You can have a piece of diamond for 10 years, it will still look like diamond. And so even though this reaction is energetically favorable according to thermodynamics, the process is so slow that it's not very useful in terms of everyday application. So chemical kinetics would describe how fast this reaction is going. It says basically it's a slow reaction. Thermodynamics basically tells us that this reaction is spontaneous, it's energetically favorable. Another example is the combustion of glucose. When glucose reacts with oxygen, it produces carbon dioxide and water. Delta G for this reaction is also negative. So this reaction is spontaneous, it's energetically favorable. Energy is released during the combustion of glucose with oxygen. However, if you were to put sugar on a table, it's not going to spontaneously combust. Glucose doesn't react with oxygen very fast at room temperature. So this too is a slow reaction. The activation energy is relatively high. So even though it's spontaneous, it's not a fast reaction unless you heat it up or add a spark to it. Same thing is true with gasoline. Gasoline doesn't always spontaneously combust in air unless you give it a spark or something to get the reaction started. So these chemical reactions at room temperature is relatively slow. So make sure you understand that chemical kinetics deals with how fast a reaction can occur, whereas thermodynamics tells you if a reaction is spontaneous, if it's energetically favorable. Now consider the reaction where A converts to B. So A is the reactant, B is the product. Now, as the reaction proceeds from left to right, the concentration of the reactant will decrease. The concentration of the product will increase. Now, we could describe how fast this reaction is going by measuring the rate of the reaction. The rate of the reaction is going to be equal to the change in the concentration of B divided by the change in time. So the square brackets indicates concentration. So we have the units molarity over some unit of time, like seconds, it could be minutes or hours. So typical unit of rate is molarity per second. It could be molarity per minute and so forth. Now we have a positive sign here because the concentration of B is increasing as the reaction progresses. But we can describe the rate of the chemical reaction with respect to A. It's also equal to the change in the concentration of A divided by the change in time. But we're going to put a negative sign in front. So by putting the negative sign in front, the reaction rate is assumed to have a positive value by definition, because the change in A is negative times another negative, which will make this positive. So for reactants, you're going to have a negative sign if you relate it to the rate of the overall chemical reaction. With products, you're going to have a positive sign. So let's draw some graphs. So if we were to plot the concentration of A with respect to time, the concentration will decrease over time. Now, how it decreases depends on the reaction. It can be a straight line or it can be a curved line. But generally speaking, the reactant will decrease in concentration over time. Whereas the product, let's use B for example, the product B will increase in concentration over time. Now let's erase a few things. The change in concentration of B divided by the change in time, this is known as the average rate of appearance of B. B is appearing. The concentration of B is increasing. If we wish to calculate the average rate of disappearance of A, it's simply the change in the concentration of A divided by the change in time. So what we would do is we will take the final concentration of B, subtract it by the initial concentration of B, and then divide that by the change in time. That is the time difference between these two concentrations. And the same is true for calculating the average rate of appearance for a reactant A. It would be just the final concentration of A minus the initial concentration over the change in time. Now let's say if we have a reaction where one molecule of A reacts with 2 molecules of B to produce 3 molecules of C and 4 molecules of D. Now we can express the rate of the overall reaction in terms of the change in concentration of A, B, C, or D. And here's how you can do it. So the rate is going to equal negative the change in the concentration of A divided by the change in the concentration of, the change in time. So that's the rate with respect to A. Now what about with respect to B? This is going to be negative change in the concentration of B divided by the change in time. But there's more to it. We need to incorporate the two. So you need to divide by 2. So it's going to be negative 1/2 times the change in concentration of B over the change in concentration of time. So this is how we can relate the rate of the chemical reaction with respect to the rate in the change of the concentration of B. Now, with respect to C, the rate of the chemical reaction is going to equal, this time it's going to be positive, since we're dealing with a product. The product increases in concentration. The coefficient is a 3. So instead of 1/2, it's going to be 1/3 times the change in the concentration of C divided by the change in time. Now for D, it's also a product, so it's going to be plus, and then it's going to be 1/4 the change in the concentration of D divided by the change in time. So let's consider an example problem. Let's say that B has an average rate of disappearance of negative 0.5 molarity per second. What is the average rate of appearance of C? And also, what is the rate of the reaction for this example? So let's calculate the average rate of appearance of C, which should be positive. So we're going to start with 0.5 molarity per second, or you can express it as moles per liter per second if you want to. But this is going to be substance B. And we can convert it to substance A. The molar ratio is 2 to 3. So the molarity ratio, so to speak, will be 2 to 3. So we could say 1 molarity per second for B, and that's actually 2. The coefficient in front of B is 2. So when the concentration, or rather when the molarity changes by 2 for B every second, the molarity for substance C will change by 3 every second. So we can cancel the unit molarity per second for substance B, and we can get the average rate of appearance for substance C. So it's going to be 0.5 times 3, which is 1.5 divided by 2. So that's going to be positive 0.75 molarity per second for C. Now technically this should be a negative value because B is decreasing, but this too should also be negative because it's still decreasing, and this should be positive. So overall, these two negative signs will cancel, giving us a positive result. So make sure you understand what this means. The average rate of disappearance for substance B is negative 0.5 molarity per second. The average rate of appearance for substance C, 0.75 molarity per second. Now let's put this number here. So we have positive 0.75 molarity per second for C. And we're going to use both numbers to calculate the rate of the chemical reaction. So the rate of the chemical reaction with respect to B is this. It's negative 1/2 times the change in concentration of B divided by the change in time. So this part right here, delta B over delta C, that is the rate of disappearance, or the average rate of disappearance for B, which is this value. So we're going to replace that with negative 0.5 molarity per second. So negative 1/2 times negative 0.5, this is going to be positive 0.25 molarity per second. So notice that the rate of the chemical reaction is going to be equivalent to the rate of the change in concentration of a substance with a coefficient of 1. In the case of A, it would simply be negative 0.25. So the rate of disappearance and the rate of appearance for each species is going to be proportional to the coefficients in front of them. As you can see, C has a change in concentration per change in time that's 3 times the amount relative to A, because the molar ratio is 1 to 3. Now let's calculate the rate of the chemical reaction, but with respect to C. It's going to be positive, we used in this equation here, 1 over 3 delta C over delta T. So that's 1 over 3 times 0.75. So here we have two positive values. The overall rate of the reaction will be positive. And we're going to get the same answer. It's going to be positive 0.25 molarity per second. So I want you to understand how this equation relates to the rate of the chemical reaction. So now you can calculate the rate of the chemical reaction with respect to any of the substances in the reaction. Now let's work on some practice problems. So in this example, we're given a table that shows the concentration of NO with respect to time. Calculate the average rate of disappearance of NO in the first 20 seconds. So what should we do in this problem? To calculate the average rate of a reaction, you need to calculate the change in concentration and divide it by the change in time. So to calculate the average rate of disappearance of NO, it's going to be the change in the concentration of NO, which is the final concentration minus the initial concentration divided by the time difference. So we need to do it for the first 20 seconds. So that's from 0 to 20. The final concentration at 20 seconds is 0.586 moles per liter, which is molarity. minus the initial concentration, which is 0.75. And the time difference is 20 seconds. So 0.586 minus 0.75, that's a change of negative 0.164 divided by 20. And so the average rate of disappearance of NO is negative 8.2 times 10 to the minus 3 molarity per second. So that's the average rate of disappearance. Now let's move on to the next problem. Dinitrogen pentoxide decomposes into nitrogen dioxide and oxygen gas as shown in the equation below. If the average rate of appearance of NO2 is 4.6 times 10 to the minus 3 moles per liter per second, what is the average rate of disappearance of N2O5? So how can we find the answer for this problem? It turns out that the rate of appearance for NO2 is directly related to the rate of disappearance of N2O5 based on the balanced chemical equation. In fact, you can use the molar ratios to get the answer. You simply need to convert it. So let's start with what we're given. 4.6 times 10 to the minus 3, and that is moles of NO2 per liter per second. Now let's convert moles of NO2 to moles of N2O5. Now, for every 4 moles of NO2 that appears or that is produced, 2 moles of N2O5 disappears. Now, you need to understand that the rate of appearance is always positive, and the average rate of disappearance is always negative, which means that the concentration of the reactants always decreases, and the concentration of the products increases as the reaction moves forward. So the rate of the reaction in terms of reactant should always be negative, and for a product, it should be positive. So I'm going to put a negative sign since we're dealing with a reactant. So these units will cancel. And so it's going to be 4.6 multiplied by negative 2 divided by 4. And so the answer is going to be negative 2.3 times 10 to the minus 3 moles of N2O5 per liter per second. So that's how you can calculate the average rate of disappearance of N2O5. Number 3, the graph below shows the concentration of Fe plus 3 with respect to time. Estimate the average rate of disappearance of Fe plus 3 in the first 30 seconds. To calculate the average rate of change from a graph, you need to calculate the slope of the secant line. So we need 2 points. A secant line touches the curve at 2 points. So the slope of this line will give us the average rate of change. Now, if we want to find the instantaneous rate of change, we need to find the slope of a tangent line. And the slope of the tangent line touches the graph at 1 point, as opposed to the secant line which touches it at 2 points. So keep that in mind. So whenever you want to find the slope of a line, it's the change in y divided by the change in x. And in this problem, the change in y values represents the concentration. So it's going to be C2 minus C1. The change in x values is the change in time. And the change in concentration divided by the change in time can give us the rate of disappearance of Fe plus 3. So this is the initial concentration, which we'll call C1, and this is the final concentration, C2. So it's going to be the final concentration, which is about 0.4, minus the initial concentration, which is 1.0, divided by the change in time, which is the first 30 seconds. So 0.4 minus 1, that's negative 0.6 divided by 30. And so it's going to be negative 0.02 m per second, or molarity per second. So that's the average rate of appearance, or rather disappearance, of Fe plus 3. So now let's briefly talk about the rate law expression. This is also known as the differential rate law, which is different from the integrated rate law. The differential rate law shows how the rate of the chemical reaction depends on concentration. The integrated rate law, which is not really covered in this video, it shows how concentration depends on time. So here's a typical rate law expression. In this equation, the rate of the chemical reaction is equal to some rate constant K times the concentration of A, let's say to the first power, times the concentration of B to the second power, times the concentration of C to the third power, times the concentration of D, let's say to the 0 power. When you see a rate law expression, you need to know what this means. The rate of the reaction is first order with respect to A. It's second order with respect to B, third order with respect to C, 0 order with respect to D. So the order for each reactant is simply the exponent associated with that respective reactant. Now, another thing you need to be familiar with is something called the overall order for the reaction. To find this, simply take the sum of all of the exponents. 1 plus 2 plus 3 plus 0 is 6. So we can say that the reaction is 6 order overall. Now, what does it mean when it's first order with respect to A? This means that if we double the concentration of A, the rate of the reaction is going to increase by a factor of 2. And the reason for this is 2 to the first power is 2. If we were to increase A by a factor of 3, the rate of the reaction will increase by a factor of 3. 3 to the first power is 3. Now what about B? What does it mean that it's second order with respect to B? If we were to increase the concentration of B, let's say by a factor of 2, the rate is going to increase by 2 squared. So it's going to increase by 4 because 2 squared is 4. If we were to increase the concentration of B by a factor of 3, the rate is going to increase by a factor of 3 squared. 3 squared or 3 times 3 is 9. So the rate is going to increase by 9. If we were to increase the concentration of B by a factor of 4, 4 squared is 16. So the rate is going to increase by a factor of 16. So that's what it means when it's second order overall. Any changes in the concentration of B, the changes that the rate will feel will be squared of what the changes that B feels. Now let's focus on C. It's third order with respect to C. So if we increase C by a factor of 2, the rate is going to go up by 2 to the third power. 2 to the third power is 8. So the rate of the reaction will increase by a factor of 8. If we increase the concentration of C by a factor of 3, 3 to the third power is 27. So the rate is going to increase by a factor of 27. I'm giving you a lot of examples because I really want you to understand this concept. Now let's focus on D. It's 0 order with respect to D. So if we increase the concentration of D by a factor of 2, what's going to happen to the rate? What would you say? 2 raised to the 0 power is what? Anything raised to the 0 power is 1. So there's not going to be any change for the rate. It doesn't matter how much we change D. Let's say if we're to increase D by a factor of 3, the rate will still not change. There's going to be no change in the rate of the chemical reaction. 3 to the 0 is 1. So the rate of the reaction doesn't depend on a concentration with a 0 order. Let me say that again. The rate of a reaction doesn't depend on a reactant that is 0 order. So in this case, for this particular example, the rate doesn't depend on the concentration of D. If you increase D or if you decrease it, the rate of the chemical reaction will still be the same. So a zero-order reactant has no effect on the rate of the reaction. The one that has the greatest effect is reactant C because it has the highest order. If you double C, the rate will greatly increase by a factor of 8. So C has the greatest effect on the rate of the chemical reaction, but D has no effect on it. Now let's work on some practice problems that involve finding the rate law expression by experiment. So in this problem, we're given a table which shows the concentration of reactants A and B in units of molarity. And we also have the initial rate of the reaction with the units molarity per minute. So how can we determine the rate law expression that fits the experimental data? So first, we need to find the order of the reaction with reactants A and B. So what you want to do is pick two trials in which one reactant is held constant, but the other changes. So if we pick trials 1 and 2, notice that A is held constant in concentration, but the concentration of B doubles. So as B doubles from 0.20 to 0.40, notice that the rate increases by a factor of 4 from 0.4 to 1.6. So you can write this expression: 2 to the what power is equal to 4. We know that 2 squared is 4, so x is 2. This means that it's second order with respect to B. So when we write the rate law expression, let's say for A, we don't know what the order is, so I'm just going to put a y variable. But for B, we know it's second order. So anytime the concentration doubles, and if the rate quadruples, you know it's second order. But if you wish to calculate the two, if you want a step-by-step process, here's what you could do. We can use the formula B2 over B1 raised to the x is equal to R2 over R1. Now, A is constant, so we don't have to worry about A. But for trials 1 and 2, B changes. So that's why we have B in this expression. So B2, or the concentration of B for trial 2, is 0.4. The concentration of B for trial 1 is 0.2. And the rate for trial 1 is 0.4. And the rate for trial 2 is 1.6. So 0.4 divided by 0.2 is 2. And 1.6 divided by 0.4 is 4. Now, if you wish to calculate x, it's going to be log 4 divided by log 2. You just got to take the log of those two numbers. And this number is always going to go on the bottom. This one's going to go on the top. Log 4 divided by log 2 is equal to 2. And so that's how we know it's second order with respect to B. So now let's find the order with respect to A. So notice that if we pick trials 1 and 3, A doubles from 0.20 to 0.40, but B is held constant. And notice what happens to the rate. The rate doubles from 0.4 to 0.8. So since A doubles, we're going to put a 2, and the rate doubles, we put a 2. So 2 is the same as 2 to the first power. So y is equal to 1. So it's first order with respect to A. Now for those of you who want to use the formula, here's what you can do. It's going to be A2 divided by A1 raised to the y, and that equals R2 over R1. But I'm going to change it a little because we use trials 1 and 3, so I'm going to write A3 over A1 raised to the y, and that's equal to R3 over R1. So A3 is 0.4. For trial 1, the concentration of A is 0.2, and that's raised to the y. For trial 3, the rate is 0.8, and for trial 1, it's 0.4. So 0.4 divided by 0.2 is 2, and 0.8 divided by 0.4 is also 2. So therefore, y is going to be log 2 divided by log 2, which is equal to 1. And so that's how we know it's first order with respect to A. So now what is the overall order of the reaction? It's first order with respect to A, second order with respect to B. To calculate the overall order of the reaction, all you have to do is simply add the exponents. So 1 plus 2 is 3. That means that the reaction is third order overall. So this is the rate law expression. This is the answer to part A. Now what about B? Calculate the value of the rate constant. So pick any trial. I'm going to choose trial 1. For trial 1, the rate is 0.4 and A is 0.20 or 0.2 and B is 0.2 as well. So 0.20 squared times 0.2, that's equal to 8 times 10 to the minus 3 or 0.008. So K is going to be 0.4 divided by 8 times 10 to the minus 3. So in this example, K is 50. Now we need to determine the units of K. So in this expression, solve for K. So K is going to be the rate divided by everything on the right except K. So K is equal to the rate divided by A to the first power times B to the second power. And we're given the units of the initial rate. It's molarity times minutes to the minus 1. So let's write that. Molarity to the first power, and then minutes to the negative 1 power. Now A is in molarity, and B is in molarity, but it's squared. So I'm going to write m squared. Now we could cancel m. And I'm going to take this m, move it to the top. So the units of K, you can write it as molarity to the minus 2 times minutes to the negative 1. Now keep in mind that molarity is moles per liter. So you can write molarity as moles to the first power, liters to the negative 1. So if we raise everything to the negative 2, that means we need to multiply every exponent by negative 2. And so what we now have is that molarity to the negative 2 power is moles to the negative 2 times liters to the positive 2. Negative 1 times negative 2 is positive 2. So we could replace m to the negative 2 with moles to the negative 2 times liters to the positive 2. So therefore, we could write the final answer for K like this. So we could say K is equal to 50 times moles to the negative 2 times liters to the positive 2 times minutes to the minus 1. It might be better to put the positive exponent first. So you could say it's 50 liters squared times moles to the minus 2 times minutes to the negative 1. And there's a lot of ways in which you can adjust these units. Now you could write it in terms of positive exponents. You could move the negative exponents to the bottom. So you could say it's 50 liters squared per mole squared times minutes, where these two are in the denominator of the fraction. So now you know how to calculate the value of the rate constant, and you know how to determine the units of the rate constant K. So now, let's focus on part C. What will be the initial rate if the concentration of A is 0.5 moles per liter and B is 0.8 moles per liter? So now we just got to plug it into the equation. So we have the value of K. K is going to be 50, and the units is m to the negative 2, which is basically, you could put that on the bottom, m squared, and then it's minutes on the bottom as well, which is minutes to the minus 1 on top. So that's K, and then the concentration of A is what we have here, 0.5 m, and the concentration of B is 0.8 m squared. So 50 times 0.5 times 0.8 squared will give us a rate of 16. Now m squared will cancel. And so the units for rate will be what we have here, molarity per minute. And so it's 16 molarity per minute or moles per liter per minute. You can describe it either way. And so that's it for this problem. So now you know how to determine the rate law expression, how to calculate the value of the rate constant, and how to calculate the initial rate given different concentrations. In this video, we're going to focus on reaction mechanisms, how to write the rate law for the overall reaction, and things like that. So a reaction mechanism is basically a step-by-step pathway by which a particular reaction occurs. And each individual step in a reaction mechanism are known as elementary reactions. So let me give an example. So let's say this is the first step of a certain reaction. A plus B becomes C plus D. So I'm going to put a 1 here to indicate that's step 1. Now, step 2, this is going to be D plus E, and that turns into F plus B. So the series of these two steps is known as a reaction mechanism. Each individual step is an elementary reaction. And we can write a rate law expression for each elementary reaction based on the coefficients that we see for the reactants of that reaction. So let's say if we want to write the rate law expression for the first step of this reaction mechanism. Notice the coefficients of A and B. It's 1 to 1. And we're going to call the rate constant associated with the first step K1. The rate constant for the second step, we'll call it K2. So this is going to be rate is equal to K1 times the concentration of A times the concentration of B. And this is going to be to the first power. So that's the rate law expression for the first step of this reaction mechanism. Now for the second step, or the second elementary reaction, the rate law expression is going to be times D times E. So that's how you can write the rate law expression for a certain step in a reaction mechanism. By the way, in this reaction, can you identify the catalyst and the intermediate? Which species represents the catalyst and which one is the intermediate? If we were to add these two elementary reactions, the catalyst and the intermediate will be canceled as we try to get the overall reaction. To distinguish the catalyst from the intermediate, you need to know that the catalyst is consumed first in a reaction and then it is produced later. The reverse is true for the intermediate. The intermediate is produced first in a reaction and then it is consumed later. So notice that we can cancel species B and we can cancel D. One of them is the intermediate and the other is the catalyst. So is B the catalyst or the intermediate? What would you say? Notice that B appears first on the left side of the reaction. So it is consumed first. Then it reappears on the right side of another reaction later. So it's consumed first and then it's produced later. That is the catalyst. The catalyst is present in the beginning of the reaction and at the end of the reaction. The intermediate is only present in the middle. It is produced first and then it is consumed later. So if you look at D, D is on the right side of step 1. It's on the right side of that reaction. So it is produced first. Then it shows up later on the left side of the second reaction. So it's consumed later. It is produced first, consumed later. So it is the intermediate. So remember, the catalyst is at the beginning and at the end of the reaction. It is consumed first and then produced later, but the intermediate is in the middle. It is produced first and then consumed later. So that's a quick and simple way that you could use to identify the intermediate and the catalyst in a reaction mechanism. Now remember, a catalyst is a substance that can speed up a chemical reaction. And the way that it accomplishes this is by providing the reaction with an alternative pathway for the reactants to become products. And another benefit of a catalyst is that it lowers the activation energy. And by those means, it can speed up a chemical reaction. So now let's write the overall reaction for this reaction mechanism. B and D has been canceled. On the left, we have A and E. So this is going to be A plus E. And on the right, we have C and F. So this is now sometimes you need to be able to determine the molecularity of each individual step in the reaction mechanism. So the first term you need to be familiar with is a unimolecular reaction. In a unimolecular reaction, if you think of the word uni means one. So we have one molecule that is going to be the reactant. So a good example of a unimolecular elementary reaction is A going into B. The rate law expression for that is rate is equal to K times A raised to the first order. The overall order of a unimolecular reaction is first order. Now the next thing we need to talk about is a bimolecular elementary reaction. So remember, an elementary reaction is simply one step in the overall reaction mechanism. A good example of a bimolecular reaction, and remember the prefix bi means two. So we're dealing with two reactants. One example is A plus A turns into B. Another example is A plus B turns into C. So both of these elementary reactions are bimolecular reactions. In each case, we have two reactants reacting with each other. So the rate law expression for the first one is going to be K times A, or we can just write A squared. And for the second one, it's going to be rate is equal to K times A to the first power times B to the first power. In each case, the overall order of the reaction in this case for each reaction, it's second order. So that's going to be the overall order for a bimolecular reaction. Now the next type of reaction we need to consider is a termolecular reaction. When I think of the prefix ter, for some reason I associate it with tri, and tri means 3. Now termolecular reactions are quite rare because it's, statistically speaking, it's difficult for 3 molecules to collide at the same time with the right amount of energy and with the right orientation for the reaction to occur. So these reactions are very rare, and they tend to be quite slow too. But here's an example of a termolecular reaction. A plus B plus C becoming D. Another example is 2A. We can write as A plus A, or just 2A plus B turning into C. Or we could say 3A becomes B. All of these examples are termolecular reactions. The rate law expression for the first one is going to be rate is equal to K times A times B times C. For the second one, we have rate is equal to K times A squared, because we have 2A, and then times B. For the last one, its rate is equal to K times A to the third power. So the order of each reactant is simply the coefficient of the reactant for an elementary reaction. You can only do that for elementary reactions and not the overall reaction. So as we can see, the overall order for each of these elementary reactions is 3. So a termolecular reaction, the overall order for that type of reaction is third order. It's third order overall. Now consider this reaction where we have O3 reacting with NO2 to become NO3 plus O2. So that's the first step. And for the second step, we have NO3 plus NO2 turning into N2O5. Now let's say the first step is slow, but the second step is fast. With this information, go ahead and write the overall reaction and determine the rate law for the overall reaction, and identify any intermediate or catalysts if applicable. So first, let's add up this reaction. Notice that NO3 cancels. Is this a catalyst or intermediate? So NO3 doesn't appear in the beginning or at the end. It's only in the middle of the reaction. It is produced first and then it is consumed later. So because it only shows up in the middle of the reaction, this is going to be an intermediate. Now let's write down what's left over. So on the left side, we have one O3 molecule, and we have 2 NO2 molecules. On the right side, we have 1 N2O5 molecule and one O2 molecule. So that's the overall reaction for this reaction mechanism. Now, how can we write the rate law expression for the overall reaction? The rate of the overall reaction is going to be dependent on the rate determinant step. Which step is the rate determinant step? Is it the first step or is it the second step? The rate determinant step is going to be the first elementary reaction because that's a slow step. The rate will always depend on the slow step. So the rate for the overall reaction will be equal to the rate of the slow step, which is the rate of the slow step is K1 times O3 times NO2. So that's a bimolecular reaction. So if they were to ask you what is the molecularity of the first step, you would say it's bimolecular because the overall order for that step is 2. We have 2 molecules reacting with each other. So this is the rate law expression for the slow step. To write the rate law for the overall reaction, instead of writing K1, we can simply write K. So we can say it's K times O3 times NO2. So K would be just a generic term for a constant for the overall reaction. But this is the rate law expression that we're looking for. So it's first order with respect to O3, first order with respect to NO2, and it's second order overall. And go ahead and try this example problem. So write the overall reaction for the mechanism shown below. Identify any catalysts and intermediates that may be in a reaction, and determine the molecularity for each elementary reaction. And then write the rate law for the overall reaction as well. So let's begin. Let's identify any catalysts or intermediates that may be present first. Notice that we can cancel iodide and we can cancel IO minus. So IO minus is the hypoiodide ion. Which one of these is the catalyst and which one is the intermediate? What would you say? So looking at I minus, it is present at the beginning of the reaction and at the end. It is consumed first and then it is produced later. So this is the catalyst. IO minus is in the middle of the reaction. It is produced first and then it is consumed later. So this is going to be the intermediate. So that's how you can distinguish from the two from each other, and that's how you can also identify them as well. So now let's go ahead and write the overall reaction. On the left side, we have 2 peroxide molecules reacting with each other. So that's hydrogen peroxide. On the right, it's going to produce 2 water molecules. And we're going to get an oxygen molecule. So the decomposition of hydrogen peroxide into water and oxygen gas is accelerated by the presence of an iodide catalyst. Now, what is the molecularity for the first elementary reaction? And what about for the second step? For the first step, we have two reactant molecules. So it's bimolecular for the first step, and it's also bimolecular for the second step. So that's the molecularity for each step in this reaction mechanism. Now to write the rate law expression, I need to tell you which one is slow and which one is fast. Let's say the first step is the slow step, and the second step is the fast step. So with that information, what is the rate law expression for the overall reaction? Feel free to pause the video and work on that. The rate law expression for the overall reaction is going to be equal to the rate of the slow step, the rate determinant step. So let's write the rate law expression for the slow step. So this is K1 and this is K2. So the rate for the slow step is going to be K1 times the concentration of hydrogen peroxide. The coefficient for that is a 1, and then times the concentration of iodide, which is also to the first power. So that's the rate law expression for the first step. But now to write the rate law expression for the overall reaction, which is this reaction here, notice that iodide is not part of the overall reaction. The overall reaction contains only one reactant, H2O2. So therefore, the rate law expression should only contain that reactant. So instead of writing K1, we can simply write K for the rate constant for the overall reaction. Even though this K looks big, this should be lowercase k. Now this part is going to stay the same. The rate law for the overall reaction is going to equal the concentration. It's proportional to the concentration of H2O2 to the first power. Now, since iodide is not in the overall rate law expression, we can get rid of it. So this will be the rate law expression for the overall reaction. And this is the rate law expression for the first step with iodide included. So that's it for this problem. In this video, we're going to talk about how to solve integrated rate law problems. So if you have a pen and a sheet of paper with you, feel free to use them to take down some notes, which is going to be useful later on as we work on some problems in this video. So let's begin our discussion with the rate law expression for each of these ordered reactions. So for a zero order reaction, the rate is equal to K times A raised to the zero power. Anything raised to the zero power is 1. So the rate is simply equal to K. A is a reactant. So think of a reaction where, let's say, A turns into B. So A is the reactant and B is the product. So for a zero order reaction, the rate of the reaction doesn't depend on the concentration of the reactant. For a first order reaction, the rate does depend on the concentration of the reactant. Its rate is equal to K times A raised to the first power. For a second order reaction, the rate is equal to K times A raised to the second power. So the order of the reaction is based on the exponent that you see here. Now, for a first order reaction, if you double the concentration of A, the rate is going to double. If you triple the concentration of A, the rate is going to triple. For a zero order reaction, if you double the concentration of A, it's going to have no effect on the rate. If you triple the concentration of the reactant A, no effect. 3 to the 0 power is 1. For a second order reaction, if you double the concentration of A, 2 squared is 4. The rate is going to increase by a factor of 4. If you triple the concentration of A, 3 squared is 9. The rate is going to increase by a factor of 9. So the order of the reaction, or rather the order of the reactant, tells you how the concentration will affect the rate. The rate of the chemical reaction is most affected by a reactant that is second order compared to a reactant that is first order or even zero order. So the higher the order of the reactant, the greater its impact will be on the rate of the reaction. Now let's talk about the units of the rate constant K. So the units of K for a zero order reaction is going to be m to the first power times t raised to the -1. Now, t is a unit of time. It could be seconds, it could be minutes, it could be hours, it could be even days. But t is some type of unit of time. Now, for a first order reaction, it's going to be m to the 0, t to the -1, or simply t to the -1. For a second order reaction, the units of K is going to be m to the -1, t to the -1. Notice what's happening to the exponent of m as you increase the order of the reactant. It's decreasing by 1. So for a third order reactant, it's going to be, the units of K will be m to the -2, t to the -1. So we can come up with a general equation that will tell us the units of K given the order of the reaction. And here it is. It's m raised to the 1 minus n times t to the -1. So that's the units for K for any order. So let's say if it's second order, n is 2. So this is going to be m raised to the 1 minus 2 times t to the -1. 1 minus 2 is -1, so you get this. So this expression is very useful in determining the units of K given the overall order of the reaction. Now the next topic of discussion is the half-life. So the half-life is a unit of time. So it's going to be t with a subscript 1/2. And that's the time it takes for the concentration of a reactant to decrease by half of its original amount. For a zero order reaction, the half-life is going to be the concentration. Let me write this better. It's going to be the concentration of A, more specifically the initial concentration of A, divided by 2K. For a first order reaction, the half-life is going to be ln2 divided by K, where K is the rate constant. And for a second order reaction, it's going to be 1 over K times the initial concentration. So what you want to gather from this is that the half-life for a first order reaction doesn't depend on the initial concentration. For a zero order reaction and a second order reaction, the half-life depends on the initial concentration. But for a first order reaction, it's independent of the initial concentration. Make sure you write that in your notes too, because that's a typical test question. Now, in all cases, the half-life depends on the rate constant k. And notice that k is always in the bottom of the fraction for the half-life equation. So that means for all cases, as the rate constant increases, the half-life will, regardless of the order of the reaction, if it's 0, first, or second order. Now for a 0 order reaction, if we increase the initial concentration, the half-life is going to increase. So for a 0 order reaction, the half-life is directly proportional to the initial concentration. Now the reverse is true for a second order reaction. If we increase the initial concentration, the half-life decreases. So the initial concentration and the half-life for a second order reaction is inversely related. For a first order reaction, if you try to increase the initial concentration, it's going to have no effect on the half-life. The half-life is not going to go up, it's not going to go down. The half-life is independent of the initial concentration for a first order reaction. Now let's talk about the equations for the integrated rate law expression. Now it's going to be tough fitting it in here, so I may have to erase it after I write it. So hopefully you have a sheet of paper and you can write it down, because we're going to refer back to these equations. So for a 0 order reaction, the final concentration is equal to negative kT plus the initial concentration. So that's the integrated rate law expression in slope-intercept form. Y corresponds to the final concentration, M corresponds to negative K, X corresponds to T, and B corresponds to the initial concentration. So notice that the slope is equal to negative K, and the y-intercept is equal to the initial concentration. So make sure you write this equation. So for the next part, I'm going to put the slope, because you want to know that as well. So for a 0 order reaction, the slope is going to be negative K, as was mentioned. Now let's talk about a first order reaction. The integrated rate law expression for a first order reaction is the natural log of the final concentration, and that's going to equal negative kT plus the natural log of the initial concentration. So once again, this is in slope-intercept form. So as you can see, the slope is still negative K. The y-intercept this time is the natural log of the initial concentration. So we can write M is equal to negative K for first order reaction. Now for a second order reaction, it's going to be 1 over the final concentration, and that's going to equal positive kT plus 1 concentration. So this too is in slope-intercept form. So we have y is equal to mx plus b. So this time the slope is equal to not negative k, but positive k. And the y-intercept is 1 over the initial concentration. So we're going to put m, the slope, is equal to positive k. Now the next thing that you need to know is the plot that leads to a straight line graph. For a zero order reaction, it's simply the concentration versus time. For a first order reaction, if you plot the natural log versus time, you're going to get a straight line. And for a second order reaction, you need to plot 1 over the concentration versus time. And the formula pretty much tells you that as well. So here's the graph for a zero order reaction. You need to have the concentration of A on the y-axis, T on the x-axis, and the graph is going to look like this. Because as you can see, the slope is negative. K is always positive, but because the slope is negative k, you can see that it's a decreasing function with a straight line. Now for a first order reaction, if you were to plot the natural log of A versus time, you would get a similar shape. It's going to be a straight line graph with a negative slope. For a second order reaction, if you plot 1 over A versus time, it's different. This is going to be a straight line graph going up. So as you can see, the slope is positive k. So that's why it's an increasing linear function. Number 1, which of the following could represent the units of the rate constant k for a reaction that is third order overall? Is it going to be A, B, C, or D? So go ahead and take a minute and try this. We know the units of k can be represented by this formula. M raised to the 1 minus n times t to the minus 1, where n represents the order of the overall reaction. So this reaction is third order overall, therefore n is going to be 3. So it's m raised to the 1 minus 3 times t to the minus 1. 1 minus 3 is negative 2. So the units for a third order overall reaction should be something to this effect: m to the minus 2, t to the minus 1. And this corresponds to answer choice C. So that's the answer for this problem. T could be anything. It could be seconds, minutes, hours, days, but it's some unit of time raised to the minus 1. Number 2, which of the following straight line plots correspond to a first order reaction? So hopefully you have your sheet of notes with you if you haven't memorized it already. But let's review the zero order reaction. So if you recall, for a zero order reaction, if you plot A versus T, you're going to get a straight line graph. And the slope of that graph is going to be negative k. So A versus T corresponds to a zero order, not a first order. Now for a second order reaction, the graph 1 over A versus T produces a straight line plot. And the slope for that is not negative k, but positive k. So we could eliminate answer choice C. 1 over A versus T will not produce a straight line plot for a first order reaction. For a first order reaction, the graph that we need is ln A versus t. It's the natural log versus time. When we plot ln A on the y-axis, time on the x-axis, we're going to get a straight line plot with a slope of not positive k, but negative k. So the correct answer is let me say that again. The correct answer is answer choice D. The slope is going to be negative k, and the graph is ln A versus t. It's not positive k. Number 3, which of the following statements is false? So let's analyze each choice. Answer choice A. The half-life of a first-order reaction is independent of the concentration of the reactant. Is that true or false? So hopefully you have your sheet of notes with you, and let's look at the half-life equation for a first-order reaction. The half-life is equal to the natural log of 2 divided by the rate constant K. Notice that the initial concentration of A is not part of this equation. Therefore, answer choice A is a true statement. The half-life is independent of the initial concentration of the reactant. Now let's look at answer choice B. The rate constant K is inversely related to the half-life of a second-order reaction. Is that true or false? Well, if you have your sheet of notes with you, let's look at the half-life equation for a second-order reaction is this. It's 1 over K times the initial concentration of A. Now notice that the rate constant K is in the denominator of the fraction. Whenever you increase the denominator of a fraction, the value of the whole fraction goes down. So as we increase the rate constant K, the half-life is going to decrease. So when K goes up, the half-life goes down. So this describes an inverse relationship. So therefore, B is true. The rate constant K is inversely proportional to the half-life for a second-order reaction. Now what about C? The half-life of a zero-order reaction is directly proportional to the initial concentration of the reactant. Is that true or false? So let's begin by writing the equation. So the half-life equation of a zero-order reaction, that's going to be the initial concentration A divided by 2K. So we're analyzing the half-life and the initial concentration of the reactant. So we're comparing these two. Notice that the initial concentration of the reactant is in the numerator. Whenever you increase the numerator of a fraction, the value of the fraction goes up. If you increase the denominator, the value of the fraction goes down. So because the initial concentration is in the numerator, there is a direct relationship. As we increase the initial concentration, the half-life is going to increase as well. So there's a direct relationship between the two. So C is the true statement. These two are directly proportional. Now what about answer choice D? The half-life of a zero-order reaction is constant. Is that true or false? So this is the half-life for a zero-order reaction. Is this value, T1 half, is it constant? So T1 half depends on the initial concentration and K. This too is not going to change. That's constant. K is the rate constant of a reaction. The fact that it's a rate constant means that K doesn't change. That is, if the temperature doesn't change. So we're assuming that the temperature remains constant. If the temperature is constant, then K is going to be constant. So at constant temperature, K is not going to change. Now, the initial concentration, is that constant? Well, the answer is no, because the purpose of chemical kinetics is to study how fast reactions are going. And if the reaction is going, as A changes to B, A is going to decrease. So as the reaction proceeds, the concentration of A will not be constant. It's going to decrease over time. So if A goes down, the half-life is going to go down with it because they're directly related. So therefore, the half-life of a zero-order reaction is not constant. So this is a false statement. Therefore, D is the correct answer choice. So note that the half-life of a zero-order reaction and a second-order reaction depends on the initial concentration of A. Therefore, the half-life is not constant for those two, because as A decreases, the half-life is going to change. As A decreases for a zero-order reaction, the half-life is going to decrease. But as A decreases for a second-order reaction, the half-life is going to increase, because these two are inversely related. Now, for a first-order reaction, it doesn't depend on the initial concentration. So because the half-life is independent of the initial concentration, the half-life is constant for first-order reaction. So answer choice D would be a true statement if this was a first-order reaction. Because ln2 is constant, K is constant, as long as the temperature doesn't change. So the half-life will be constant for a first-order reaction, but it's not constant for a zero-order or a second-order reaction. For the sake of learning, let's analyze answer choice E. The half-life of a second-order reaction, so we're dealing with this equation, is inversely proportional to the initial concentration of the reactant. We know that's a true statement. Now, when we were analyzing part B, we were focused on K. Anytime you increase the denominator of a fraction, the value of the whole fraction goes down. So anything on the bottom of the fraction is going to be inversely related to whatever is equal to the entire fraction. So as we saw in answer choice B, if we increase the rate constant K, the half-life of a second order reaction will decrease because it's on the bottom. So those two are inversely related. The initial concentration of the reactant is also on the bottom of that fraction. Therefore, if we were to increase the initial concentration of the reactant, the half-life would decrease. And if we were to decrease the initial concentration of the reactant, the half-life would increase. So because these two are on the bottom of the fraction, they are both inversely related to the half-life for a second order reaction. Number 4, the initial concentration of a reactant in a zero order reaction is 0.75 m. The rate constant K is 0.015 m per minute. What will be the new concentration of the reactant after 15 minutes? So feel free to pause the video if you want to try this problem. So we're dealing with a zero order reaction. The straight line equation for a zero order reaction is the final concentration is equal to negative kT plus the initial concentration. In this problem, we're given the rate constant K. It's negative 0.015 molarity per minute. The time is 15 minutes, so that's T. Let's put that in parentheses. And we're given the initial concentration, which is 0.75 m. Our goal is to calculate the final concentration 15 minutes later. So we could cancel the unit minutes, and so we're going to get the unit in molarity. It's going to be negative 0.015 times 15 plus 0.75. So the final concentration after 15 minutes will be 0.525. And it makes sense because as the reaction proceeds, the concentration of the reactant should decrease. It decreased from 0.75 to 0.525. So that's the answer for part A. Now let's move on to part B. How long will it take the concentration to be reduced to 0.06 m? So this time, we're looking for T. Let's write down what we know. We know the initial concentration is still 0.75 m. We still have the rate constant K is 0.015 molarity per minute. And the concentration is going to 0.06. So that's the final concentration, the new final concentration at some time t. So we're trying to calculate that time t. So let's replace the final concentration with 0.06 m, K with 0.015. We're trying to calculate T and then plus the initial concentration of 0.75. So let's do some algebra. Let's subtract both sides by 0.75. So these will cancel. 0.06 minus 0.75, that's negative 0.69. And the units is molarity. And then it's going to be equal to negative 0.015 molarity per minute times T. So let's divide by this number. So T is going to be negative 0.69 divided by negative 0.015. So T is equal to 46. Looking at the units, we can see that molarity cancels, and T is going to be in minutes. So the final answer for part B is 46 minutes. It's going to take 46 minutes for the concentration to go from 0.75 to 0.06 m. Number 5. Calculate the initial concentration of a reactant that took 4.7 minutes for it to reach a final concentration of 0.15 m. And we're given the rate constant K. So what do you think we need to do here? Well, let's write down what we know. So we don't have the initial concentration. This is what we're looking for. We do know the final concentration. That is 0.15 m. And we know the time that it takes to go from the initial concentration to the final concentration. And that is 4.7 minutes. And we also know the rate constant K. Instead of rewriting it, I'm just gonna highlight this. So how can we calculate the initial concentration? Well, first we need to determine which integrated rate law expression we need to use. And to do that, we need to determine the order of the reaction. Is this a zero order reaction, a first order reaction, or a second order reaction? So this problem is a little bit harder because we don't know what order the reaction is. How do we find out? Well, it turns out that we could find out from the units of K. The units of the rate constant K can help us to determine what the order of the reaction is. So the formula that we've used before to get the order of the reaction with the units of K is this one. Now, T to the minus 1, we have that already. That's S to the minus 1, so we don't need to worry about that part. What we're going to do is we're going to set this equal to this part of the unit, m to the negative 1. So that means that 1 minus n is equal to negative 1 because m equals m. Our goal is to solve for n. N is going to give us the order of the reaction. So let's subtract 1 from both sides. These will cancel, and we'll get negative n is negative 1 minus 1, which is negative 2. Multiplying both sides by negative 1, we get that n is 2. So we're dealing with a second order reaction here. Now that we know the order of the reaction, we know which integrated rate law to use. So this is going to be the equation. 1 over A final is equal to positive KT. Remember, the slope of a second order reaction is positive K, and then plus 1 over A initial. So now we could solve for this variable. Let's plug in everything else. So A final is 0.15. K is this value here. So that's 0.0025. Now we need to be careful because notice that K, the rate constant K, has the unit seconds. Here, the time is in minutes. So let's convert T from minutes to seconds. So we have 47 minutes. Always make sure that the units match. And then there's 60 seconds in 1 minute. "47 times 60 is 2820 seconds. So let's put the units here. So this was m to the minus 1, and then s to the minus 1. And then we're going to multiply that by 2820 seconds. So s and s to the negative 1 will cancel. So we're going to get m to the minus 1 here, which is 1 over m. And this is what we're looking for. One divided by 0.15, that's 6.6 repeated. So it's 6.667. And then 0.0025 times 2820, that's 7.05. Now I need to make a correction because I multiplied 47 minutes instead of 4.7 minutes. So it's 4.7 minutes times 60, which is 282 seconds, and not 2,820 seconds. So I need to get rid of this 0. So that's 282 seconds that should be here. Now if we multiply these two numbers, 0.0025 times 282 seconds, the seconds will cancel, but instead of getting 7.05, we should get 0.705. So now let's subtract both sides by 0.705. 6.667 minus 0.705, and that's going to be 5.962, and that's equal to 1 over the initial concentration. Now, once you get to this part, the quickest way to solve for the initial concentration is to take the reciprocal of both sides of the equation. To do that, raise both sides to the -1. When you raise this to the -1, the fraction flips. It flips from 1 over the initial concentration to the initial concentration over 1, which you could simply write initial concentration of A. Now here, this was 5.962 before. When you raise it to the -1, it becomes 1 over 5.962. So if we take 1 and divide it by 5.962, we're going to get the answer that we're looking for. So the initial concentration of A is 0.1677 m. So this is the answer to the problem. So when you get questions like this, if the order of the reaction is not specified, take a look at the units of K. If you're given the units of the rate constant K, you could determine if it's 0 order, if it's first order, or if it's second order. Now let's move on to our next problem, number 6. The data table below shows the concentration of a reactant with respect to time for a 0 order reaction. What is the value of the rate constant K? Now what you need to know is that the rate constant K is equal to the slope of the line if you plot A versus T for a 0 order reaction. If you plot this on a graph, you should get a straight line. So A is on the y-axis, time is on the x-axis, and it's decreasing, which means that the slope is negative. And K has to be a positive number, so K is equal to the negative slope, or slope equals negative K. So let's calculate the slope. The slope is the change in y divided by the change in x. So the y values are concentration values, and the x values are time values in this example. So let's just pick two numbers. Let's use the first and the last result. So the final concentration is 0.16, and the initial concentration is 0.8. The change in time is 40 seconds. So 0.16 minus 0.8, that's negative 0.64 divided by 40. And so it's going to be negative 0.016 molarity per second. So that's the slope, which means that K is positive 0.016 molarity per second. So remember, the slope is equal to negative K. K is always a positive number. Number 7. What is the half-life for a reaction with a rate constant K of 0.0045 seconds to the -1? So what do you think we need to do here? Well, the first thing that we need to do, like the last problem, or rather 2 problems before that, is we need to determine the order of the reaction because it's not given to us. So like problem 5, we need to pay attention to the units of K. So based on those units, s to the minus 1, what is the order of this reaction? So we know the formula is going to be m raised to the 1 minus n times t to the minus 1. And we're going to set that equal to the units of K. So this is a unit of time, and the same is true for that. But we don't see an m here. If you don't see an m, it's really m to the 0, because anything raised to the 0 power is 1. So what we're going to do is we're going to set the exponents of m equal to each other. So 1 minus n is equal to 0. If we add n to both sides, we get that n is equal to 1. So this is a first order reaction. When you don't see units of molarity or moles or liters, if you just see time to the negative 1, that's an indication of a first order reaction. So anytime the rate constant K has units such as s to the minus 1, minutes to the minus 1, hours to the negative 1, with no molarity, no moles, no liters, you know you're dealing with a first order reaction. So now that we know the order of the reaction, what formula can we use to calculate the half-life? The half-life equation for first order reaction, it's equal to the natural log of 2 divided by the rate constant K. The natural log of 2 is 0.693147. The rate constant K is 0.0045 with the unit seconds to the minus 1. So let's go ahead and divide those two numbers. So we get that the half-life is approximately 154 seconds based on the unit that we have here. So that's how we can calculate the half-life of a first order reaction. Number 8, which of the following straight line plots?
Okay, we will cut.
In this video, we're going to talk
We'll
about
cut
how
this
to
one.
solve.
It's already time, no? We'll just continue this next meeting na lang, no? The same. Taas pa na itong video. We are going to finish the PPT next meeting, and then we are going to finish also this review discussion, no? This video one. I hope you understand or you learn or you recall everything about your kinetics, no? Okay. Okay, please open your microphone for the attendance, for our attendance. Where are we? Abarkis. Abarkis. Dalawag tang. Abrasaldo.
Present, sir.
Nalit ka ganiha, Abrasaldo.
Nakasud kog 310, sir.
Okay pa na siya. Anchita.
Present, sir.
Present,
Late
sir.
po, 10
Late
minutes.
po, 10 minutes.
Nalit ka?
Yes, sir, 10
Yes, sir,
minutes.
10 minutes.
Arong.
Present, sir.
Barrios.
Various present, sir.
Silvestre.
Present, sir.
Niete.
Present, sir.
Caballero.
Present, sir.
Ñares.
Present, sir.
Clemente.
Present, sir.
Hoyos.
Present, sir.
Dakay.
Present, sir.
Biglasa.
Present, sir.
Binopol.
Present, sir.
Perham.
Present, sir.
Caryo.
Present, sir.
Pablike.
Present, sir.
Figueroa.
Present, sir.
Giliena.
Present, sir.
Jarina. Jarina. Nagluto lon. Lagroma.
Present, sir.
Leopando.
Connecting si
Kasi reconnecting si.
Karina. Siya kadali.
Okay.
Excuse me, sir. Si Abarkas
Kinsa?
po daw, sir. Connecting pa.
Okay.
Unstable ilang connection, sir.
Lagi. Leopando.
Present.
Luwab.
Present.
Present, si
Kinsa. Luwab na. Luwab. Excuse
Sir.
me.
Present, sir.
Okay. Lumibaw. Lumibaw. Wala. Sophia.
Na-excuse, sir.
Oh. Okay. Miuli.
Present, sir.
Murok. Murok. Wala. Bebida.
Present,
Hello?
sir. Narbida.
Okay. Saron. Paalis.
Present, sir.
Pipito.
Present, sir.
Iris.
Present, sir.
Andas.
Present, sir.
Punti.
Present, sir.
Rubin. Rubin?
Present, sir. Bin, sir. Present, sir.
Okay. Sanoy.
Present sana, sir.
Nilio.
Present, sir. Sinilio.
Suson. Jenny Suson, oh. Toledo.
Present, sir.
Gara.
Present, sir.
Taon.
Yaon, present, sir. Yaon, present.
Okay, kisa may na. How about Morok?
Reconnecting po daw, sir.
Morok.
Excuse me, sir. Anjeta po.
Anchita.
Si Morok, sir.
Ha? Anchita naman, Anchita, di ba? Late.
3:10 po ako pumasok, sir.
Kinsa si? Anchita?
Anchet. Opo.
Okay. Kisa ni? Suson, wajud ni no? Wajud. So siya lang na absent karon. Okay, so tomorrow I think we don't have a class, no? Correct ba? No?
Yes, sir.
Okay, so again, shout out to Abarkis and to Iscario Jan, no? For getting a very high score sa ato ang first quiz, no? So we will be having our next assignment pertaining to this review on the chemical kinetics. I hope you understand more, no, on this discussion, no. I like the way the organic chemistry guys discuss the topic, no. Pare-pareha gyud sa gusto nako nga ma-input sa inyo, ha. Okay? So galing kay doon ay mga error nga uban pero okay lang, no, yaran pong correctional. Okay, so we will continue by Thursday, no? Thursday again. Thursday ba to? Yes, Thursday. Okay. So if you don't have any question, guys, you can log out now. Okay.
Thank you, sir.
Okay.
Thank you, sir.